Let's talk more about the physical nature of current. As you can see from this picture, electrons in a wire are in constant motion, and this motion is it's a random motion. So electrons are constantly moving. They collide with one another and with other atoms of the wire. And if there is no electrical field and electrons are following the zigzag line motion, there is no current, because if you look at every velocity of those electrons in the wire, the average velocity would be 0. When a battery is connected into electrical circuit, electric potential difference is established. If we have an electric potential, then we are going to have an electric field, E, that is just equal voltage difference divided by the distance. When we have an electric field, we are going to have an electric force, and that gives the electrons a net motion. The velocity of this motion is called drift velocity. What actually is happening? Electrons are still continue their zigzag motion, as you can see in this picture. However, on average, they start shifting to the left. So they still kind of collide with each other, collide with other atoms, but there is something happening with outside this random motion. If you sum up all the velocities of the electrons, all those vectors, the sum is not going to be 0 anymore. It's going to become a net velocity that is drift velocity. I'm going to ask you a question. If we know a current, can we calculate drift velocity? Or if we know drift velocity of electrons in the wire, can we calculate current? Yes, we can do it, and there is a simple derivation. And let's just give me a little bit of space to write. So, and then how are we going to do that? As seen in the picture, we have a cylindrical wire of cross-section A, and electrons moving inside this wire with a drift velocity Vd. So the current, by definition, is equal amount of charged travel out of one end of the wire per unit time, delta T. Amount of charge is also can be calculated as electron charge multiplied by number of electrons that going out one end of wire in time delta T. So how much electrons are actually going to leave? Let's define who's going to leave is those electrons in the gray area. So if we define electron density as number of electrons over volume, we can write it's like that: N A times L. L in this case is this distance, L, so it's N drift velocity delta T, and I forgot to write area over here. So from this equation, number of electrons is equal electron density times area times drift velocity times delta T. Then let's plug it in into equation for current. Current then is equal, delta Q is E times N over delta T. Let's plug in the expression for N. Electron charge, little n, A, Vd, delta T divided by delta T. Delta T cancelled out, and we'll get expression E, N, A, and a drift velocity, Vd. I'm missing negative sign. Negative sign comes from the fact that electrons moving into opposite direction of current. So if Vd goes to the right, then current goes to the left. So that's how minus sign come around. So we should put it over here. We should put minus sign. And okay, so here is our expression. The next important relationship in our lecture is Ohm's law. It's established relationship between current and voltage. It's been noticed that under normal condition, current is always proportional to the voltage. So if voltage gets larger, currents get larger. If currents get larger, voltage gets larger. And coefficient of proportionality between voltage and current is called resistance. I personally like this form of Ohm's law. Voltage is equal current times resistance. However, this is exactly the same relationship. If you just divide this one by resistance, we'll get equation for the current equal voltage over R. So we'll get Ohm's law. It'll start here. Okay. The units of resistance are ohms, and we're using this fancy omega letter. So I usually do it this way. So ohms is equal volts divided by ampere. In the previous slide, we defined resistance, and we had the voltage is equal resistance multiplied by current, and resistance was coefficient of proportionality between voltage and current. So if we know voltage, we can divide it by current, hence calculate resistance. So there is a second way to calculate resistance. If we know what material it made of and its dimension, its size. So it depends on the material. Obviously, some material conductors are better conductors or worse conductors, and there is a concept called resistivity. Don't confuse it with resistance. We're using letter ρ for its notation, and it depends only on the material. It's been derived experimentally that resistance is proportional to resistivity, is proportional to length of the conductor, and it's inversely proportional to area, cross-sectional area of this conductor. So we have two ways to find resistance. Just have voltage divided by current, or if we know material and we can measure it, we can use this formula. Final notes on Ohm's law. Ohm's law predicts a linear relationship between current and voltage. That works in normal conditions, but sometimes it doesn't. It's not a fundamental law of physics. And because, as I just said, because sometimes it doesn't work. And many materials obey Ohm's law, but not all. Also, under certain condition, materials stop obeying Ohm's law. Resistors do obey Ohm's law, and they can be used as a basis for circuit ideas. Here is a picture of different resistors that you can buy in Radio Shack or use in a physics lab exercises. So they can be made in many shapes and many sizes with different resistance value for different purposes. So each of them will have a resistance proportional to the current through and potential across the resistor. In the circuit schematics, we're going to use this symbol for resistor. And as you remember, that symbol we used for battery. So in picture B over here, it shows us actual battery connected to resistor. And picture A shows a schematic of it, a circuit diagram. It's a good approximation for wires, that wires are as ideal resistors, and we assume that there is no resistance in the wire, or we can kind of also suggest that all resistance in this setup is located at the place of a resistor. And the last slide for this part of the lecture is table 19.2, where we're listing all the symbols for batteries that we can now understand what electrical circuit means. So let's just go one step at a time. Battery, we're using this symbol. Long line for positive potential, short line for negative potential, and this is the connecting wire into the circuit. Resistor zigzag line. Capacitor, two straight lines, similar to the battery, but just lines are similar lengths. Switch is a key. That's what we're using to close the circuit, open the circuit, like turn light on or lights off in the room. Light bulb. Sometimes we're just going to use a resistor instead of the light bulb, but there is a notation for light bulb. Wire, so you've seen just a single line. And those are connections, or as I call junction, wire junction. This is when current going to split two ways. If current goes this way, there is a junction. It goes up and down, or right and left. And there's going to be a law concerning how to deal with junction. And this symbol means electrical ground. That we are taking actually one wire, putting it in our circuit, whatever it is, like bulb, and connecting it to the ground. Okay, that's it. In the next part, we're going to solve 3 problems, and we're done with this lecture.